Yes, everyone has the ability to unmute themselves. They can also post questions or comments in the chat.
Okay.
And
yeah. Okay, so I hope everyone can see that. Yeah, so let's use the chat. I think since there's quite a few of us, to sort of minimize everyone talking at the same time. Maybe I'll try to play the moderator role. So there's a chat on the right there. If you clicked on chat, it'll open up, and I can send a text message there, so everyone should be able to see that. So what I was thinking we could do, I guess, so we have Priya, I see. Do we have has the LA.EPRI team come back yet? Okay, so not yet, but so when they come back, I guess what I was thinking we could start by doing, since we didn't really have time to address questions in the first session in the presentations, I was thinking we could start by taking a few questions, and maybe we'll start with Priya because there were a couple there, and then sort of the goal of this session, I think, is to identify some grand challenges that EPRI can issue, and these are sort of areas for collaboration that need to be addressed collectively. And I think one of the things that was really nice in the presentations that we had in the one that I was moderating just before the break, is that we had sort of a voice from academia and a voice from industry about challenges. Well, and I guess so Priya helped us a lot because she gave us 3 big challenges that she thinks we have on the academic side. When the LA team comes, maybe I'll ask them what they think about challenges on their side. I thought it was fascinating to hear about plans, but I think it would also be interesting to hear a bit about what are challenges they're facing, or what are challenges that they think they will face, not so much next year, but in the coming decades. I think that's really the sort of challenge we're looking for here. But so before we do that, before we go into that, so Priya, there was a question. Let me pull it up here, and I know you answered to me, but I'm guessing at least the people who asked the question were probably interested in this. So the question was about neural networks to predict loads, to make a forecast for loads, and I think the question, I guess I'll reread the question text here. It was, do you think neural networks are more useful to predict load forecast? If yes, why? Thoughts about other machine learning algorithms which would be coupled with neural networks to improve. So do you want to comment on that?
Yeah. So I think the basic idea is, I think often people ask, what is the best machine learning method to use here? Should I use a neural network to forecast load? Should I use an SVM to forecast load, or a decision tree? And I think at a first order level, it either doesn't always matter, or there isn't a clear-cut answer, because it depends quite a bit on the quality of the data that's being given to the algorithm, the volume, and also the horizon at which you're forecasting. So for example, different methods require sort of different amounts of data in order to perform well. And different methods also will be more sensitive to, for example, kind of, lower frequency or fluctuations in various kinds of demand profiles versus higher frequency fluctuations, which can then affect how good they are at various horizons of forecasting. So I think it's less a question of, when is a neural network just going to be better, and versus just sort of, what does my actual data look like? What does my actual context look like? Now, a lot of people will kind of ensemble different methods. So they'll have, a neural network that's fit to data, and a decision tree that's fit to data, and an SVM, and then they'll sort of combine all of them together. And that does tend to have better performance than just using one model alone. But it does require more computation, because you fundamentally are taking a lot more models and sticking them together. So yeah, there's always a bit of a trade-off, and I think there's never kind of an easy answer. And I also can stick a resource in the chat that's sort of an overview of load forecasting techniques, kind of from machine learning and not, that I think does a better job than I just did of sort of going over some of these points and giving some examples.
Yeah, please do. I think that would be useful. Okay, and so maybe just to restate sort of what I heard from you, Priya, in terms of challenges, and I think that was kind of the outline of your talk, but challenges for the academic side that you see around decarbonization, demand response, customer engagement. So the 3 that I heard, and stop me if I'm getting this wrong, but one was, how do you put in physics, and when you, and mostly there you were thinking about constraints, when you're solving problems like ACOPF, and I guess ACOPF is the big power system canonical, sort of problem, but there are a lot of other optimization problems around the power system, around the energy system more generally, that involve physics. So how do you put those in, and how do you handle that? And especially in the context of machine learning systems where there's a lot of promise, but often sort of off the shelf machine learning algorithms don't really think about the physics so much. And when you're thinking about managing a power system, having it not explode is probably important. So that was one. The second one I think was so I guess you said this a couple different ways. I guess the way I heard it most was interpretability question. And so you started off by saying this is around customers, and I guess in our three topics there, the place, this really is about demand response and customer engagement. Well, mostly about customer engagement, but also customer engagement during demand response. And there, it's sort of how do we turn the black box that are these machine learning AI algorithms? How do we get outputs from there that we can understand? That they go to physical quantities, and I guess that's pretty linked to the first challenge. And I actually do think there is some theoretical work to be done there as well. On how do we make that better. And then the third one, which I think we didn't have so much time of talking about, or at least in the previous session, what you were calling the distribution shift. That's something I'm personally very interested in. And so I was hoping we could talk about it in this breakout session a bit as well. And I guess so we just to restate what you were saying when you were talking about the distribution shift. You're not talking about the distribution system. You're talking about uncertainty. You're talking about if I'm looking at the distribution for temperatures, in Palo Alto today, and okay, so I can plot the histogram for what I think the temperatures are going to be on a hot summer day. Or I mean, I guess here it's more sort of late spring day in Palo Alto. If I go 20 years into the future, that histogram will likely be different. That's one of the things that the climate change papers that I'm reading are telling us. One of the sort of the phrases that I hear a lot are things like the tail of the distribution is getting fatter. But what that means is this distribution is changing. And I think one of the big challenges I see associated with that, is, and that was the sort of one of the two threads I was going to lead off of at the end of the last session, is when you think about design of infrastructure. When you think about designing these big energy systems, making these investments for the next 20 years. I think there's actually a nice echo to that in the LA DWP presentation when they were talking about EV growth, and they were saying plus 30% of load due to EVs. And I think this was looking at 2050, or it was 2030. I'm not sure but sort of we're really talking about decadal timescales there. So now if you're planning a system around that, what do you do? And what kind of tools do we have on that end? I guess maybe do you have a thought on that, Priya, before I sort of open up to the rest of the group? What tools are available on the academic side to really think about that kind of problem, or is this something that just we don't really have?
Yeah, I think in some ways we do and we don't. So I think we have things like, climate models that can do longer term forecasting, but not at a temporarily granular scale. Then you have numerical weather prediction models, which also tend to resolve these kinds of, weather physics, etc., but generally not in a way that's well tuned to forecasting things like power production or demand. They're just tuned in a different way, and they're usually good at medium scale. And then you sort of have short term forecasting through machine learning methods. So I think in some sense, there's at least something that you can do in each of these horizons. Now, none of these are particularly amazing. So there's been some work on the machine learning side, for example, to some of the stuff I was talking about like inserting machine learning into engineering and physical models. There's been some work that's tried to, for example, approximate portions of climate models in order to make them slimmer to run, so you can predict things at a kind of more granular spatial resolution. And there's been some work that's tried to more fundamentally combine numerical weather prediction and machine learning as well. So I think basically the base components exist, but I don't think we've creatively combined them yet in a way that actually allows us to have these kind of ready to go tools for some of these like longer term forecasts.
What about the rest of the group? And I guess so. One thing, so I do think, and I see Jeremy's here, so he can confirm if if I'm wrong here. But I think that this session is supposed to be an interactive version of the breakout more of a discussion. So I guess one thing I would maybe say, is I would encourage you, if if it's technically possible, to turn your video on, and don't hesitate to jump in, whether on the chat. Or okay, and I guess so. VJ, so you say I think was referring to more unexpected shifts. So I guess how would you treat those differently? The unexpected shifts versus the normal. I guess is there something fundamentally different between the two? Not normal predictable pattern. So I guess the variable I'm thinking of, when we're talking about these distribution shifts, I guess that's the first one I was thinking of was temperature. But I guess I'd also be curious to hear, are there other variables we're thinking about, where we think the distribution is going to change? That's one question for me. And then, specifically for what VJ was referring to.
Yeah, I can.
Yeah, can you elaborate on that?
Yeah. So basically, I think Priya took the example of, I think, COVID. And when you say COVID, so if you look at the climate, the effect on the weather, I wouldn't say climate because that's a long term, but the sky was so clear, especially in India, you can see clearly Himalayas, right? So I think, that was unexpected shift in the weather pattern, if you see that way, as opposed to, you can always predict temperature changes or 10 years based on how it changed last 10 years. And what Priya is saying, it makes sense, is it is bit of both. So the models basically should take care of both patterns, like unpredictable as well as predictable shift.
Right.
Yeah,
oh, sorry, go ahead, Priya.
Okay, maybe to even jump in, and I think the way you would also go about dealing with both of these is a little bit different. So, for example, in terms of longer term shifts, like, for example, due to climate change that we sort of know how to model, but aren't necessarily reflected in historical data, I think that's where there is really a role for sort of integrating physical insights and physical intuition into machine learning models so they can sort of resolve both the data and the physics. Whereas when you have some of these sort of unexpected patterns or really kind of like sharp distribution shifts, I think that's also where things like transfer learning or low data learning or zero shot learning, all of these kinds of paradigms come into play, where sort of based on historical data that doesn't necessarily reflect the current situation and just a couple of additional examples that do reflect the current situation, they can sort of quickly adapt to something that happened unexpectedly. So I think the paradigms you look at in both cases are a little different as well.
Yeah, thank you.
And I guess so maybe to push on that idea a bit. So what kinds of problems, so we talked about the weather, or I guess Vijay said, and I think he's right, more the climate, and I guess the big variable I was thinking about there was temperature, but there are probably others. And sort of one of the problems I can see where you would care about this is, I guess to put it in the context of the previous presentations, I'm LA DWP, and I need to build the power system that's going to accommodate, the increase in load from the EVs, and some amount of that I'm going to be able to do some smart scheduling, and so it won't be plus 30%, but still I need to make the system bigger, and I need to think about that. So that's kind of one problem I can think about where this matters. Are there, can we think of other problems, and other variables possibly where you have this this issue? This shift in this change in distribution. Can someone, I guess, so sorry, I'll pause for maybe 10 seconds. Someone has an idea. I think I have another idea, but it's not fully formed.
Well, Jacques, if I could add to that, I think, one area when we talk about building common data sets too, where we could share data such as about weather and weather predictions. Another may be about battery materials, and then how, as Priya was talking about, this work, the physical world meets, our AI world, and is when you consider about optimization of batteries, there are a number of physical factors, so the materials that are in the batteries, but plus, even as we mentioned, weather and temperature can affect the optimal use of a battery. And when we think about how important it is to bring renewables onto the grid, batteries are such a critical component, and our ability to optimize them, and all the right timing and the best timing for storage and for taking the power as well. So I don't know if you have any ideas about that in the group, but that is an area I think of interest, and also where there's great success in bringing renewables on board, but then it's all about the optimization of them too.
So I guess one thing that so batteries, I think, are a very good idea here, and I guess so what this makes me think of, and I'd be curious to know, Cheryl, is this where you were headed? Is, I guess, the part of the I guess the variable that I see as something where the distribution is shifting over time, it might change when you're planning, is, I guess, okay, so I guess the problem that you're solving is, how do I operate the batteries, and how do I plan for the grid in which I will be operating the batteries optimally in 2030? That's kind of the generic problem that you're solving. And what's changing is, today I can go out, I can do a survey, or I can ask an industry, what does the degradation of the battery looks like, so I can have some information, and possibly distributional information about what the performance of the batteries is. But between now and 2030, there's going to be some technological change. There are going to be improvements in batteries. Maybe there's going to be a new type of flow battery, that much more efficient than what we had before. And so somehow, when I'm thinking about how to manage the batteries in the context of the power grid, one of the things that I have to take into account there is not only the weather, the one we were talking about before, but also there are all these. So you were saying these physical factors, and I guess just to press a bit more on those physical factors, what I'm hearing when you say physical factors are, what's the chemical, what are the chemical processes happening inside the battery? And how is that changing over time? And if I move to a new type of battery, how is that going to change somehow? When I'm making decisions about how many batteries to put in, or to plan for in the 2030 power system, some kind of information about that is going to be useful. Is that what you were thinking of when you were saying physical factors?
Yeah, exactly. So one, just the physical, makeup, the composition of the battery, and the materials in the batteries are changing, and changing rapidly. And like you said, in this 10-year horizon, that's something that we can expect. Harder to exactly plan for and to model, but you can expect those changes and improvements. I think another area is that even with the batteries that we have now, we don't have a really good understanding of how to optimize them, and actually they're generally probably sub-optimized in that we don't know when we're getting towards the bottom of the power load there. And so in exercising a tremendous amount of caution, we don't draw on them as low as we probably could. But that is also probably a problem that AI could address. So how do we better utilize our batteries that we have now, the battery technology we have now, and how do you model new battery technologies coming on board in the future?
Maybe actually, could you expand a bit on that? So setting aside the sort of how is the battery going to change in the future, what are the things that make it difficult to optimize the battery today? Sort of like, what are the ways in which, and I guess, can we think of, what's different about a battery that, from sort of other components of the power system, traditional components of the power system, that make it much more difficult to optimize than the rest?
Yeah, and I would defer to some real technical experts on the line today. But from what I've heard from a number of electric utilities, is that we just don't understand very well how far we can draw them down without either doing some damage or making it more difficult later to refuel it, you know. So just as problematic and hard to, very difficult to estimate.
Mm-hmm.
Yeah, so referring to things like maybe like battery state estimation and also like remaining useful life estimation and degradation is, I guess, another difficult one, which is, you know, if I do some optimization action today, will it overall reduce the number of years I can use this battery? And I think totally agreed that those are difficult.
Thank you, Priya. Yeah, you have the exact right language. That's why I said I'll defer to some technical experts on the line today.
Mm-hmm. Mm-hmm. Yeah,
Jack, if I
thanks.
can pose another distribution shift one real quick.
Yeah.
Yeah.
Of
So I'd hinted at this during the talk, but I think so there's sort of distribution shift in time, and then there's distribution shift sort of among entities and geographies. So I think let's just use, like, using the example of predictive maintenance, I think there are lots of different entities that are starting to, for example, take drone footage of their power lines and then analyze that in order to, you know, preemptively detect any faults. But sort of what the power lines themselves look like in different locations are different. And as a result, in some sense, the models that you learn to try to predict what's going on there are going to be different. And if you kind of create a model with one utility and you try to immediately port it to another utility, it may not work. And so I think this is another, just even in the present time, how do we deal with sort of the different underlying physical realities and also the different kinds of data or quality of data we may have between different entities?
Right. And I guess more generally what you're saying is, you know, sort of to make this more general than the predictive maintenance with the drones, it's sort of if LADWP, you know, has a great algorithm to do, you know, something, you know, how do you know, and you want to move that, you know, even just to CAISO, you know, or I mean, sorry, CAISO, I meant PG&E, you know, sort of like and you know, just a bit north, you know, how do we know that this is still applicable, you know, and if you want to move it, you know, to the east of the US or, you know, a completely different country, does it still work? You know, I think that's a very good point. So I guess it's a shift in distribution in time. You know, that's the one I was thinking of a lot when you were talking. But I guess there's the space, the spatial aspect to it as well. Yeah, I think that's a very good point. So I think some of the team from LADWP are with us now. I see Hassan. And I see, I thought I saw Maria. Yeah, I see Maria. Okay, so I'm not sure exactly when you joined. One of the things I was saying in the beginning is that there were a couple leftover questions from before, and I wanted to start with those. You know, and then we kind of started talking a bit about this distribution shift question. Since you're back, I know there were, so I had at least two questions written down here that I think maybe we could follow up on quickly. So I guess one question, so Hassan, I see Hassan, can you hear me?
Yes.
Perfect. Okay, so there was a question for you when you were talking, which was, what's the role, you know, what's the role for AI in your demand response program? And maybe I'll, you know, so that was the question. I'll add sort of a tiny bit onto it, is what's difficult, you know, sort of in your demand response program, what are things where you think, you know, this is really, really hard, you know, like, you know, if only, you know, I had a better solution to do X, you know, what would X be?
Yes, good point. I would say optimizing the incentive structure. I talked about two types of DR. We have generally, excuse me, incentive-based DR and price-based DR. In the incentive-based DR, we set the incentive level, then we control the customer's device, whether it is thermostats, EV chargers, or their load. If we're automated, like with our commercial DR, we're not automated, we're manual, so the customer does it for us using their own building energy management system. With the residential DR, and I think I better say this now, that we call it in LA Power Savers. If you hear the name Power Savers in Los Angeles, that's our residential demand response program.
And today, how many do you have in that program?
BYOT type. I'm
Can
sorry?
you remind us, you said that in the previous session, but can you remind us today, how many people do you have in the Power Savers?
We have about 28,000 devices,
Today.
thermostats, that comes from about 24,000, about 500 people. Some of them have multiple devices. And we allow up to as many as they want to enroll, but we only incentivize them for 2. They can bring 5 if they want to, but they get rebates and incentives for only 2 of those. So
and examples of devices are thermostats.
Yes.
What else?
At this point, they're all thermostats. We're thinking about
thermostats.
EV chargers and batteries. Actually, one of the questions I was going to ask from the panel what's the latest technology out there with respect to, I'm answering the question now, but I'll come back to that, with the latest controlling the batteries remotely to see how we can control those batteries. And what is it we're controlling? Is it the charge rate, discharge rate, and how can we dispatch it using the technology? That would help us a great deal if we want to bring batteries and EV chargers into the demand response program. Yeah, with the one we have at this point is the BYOT type, and we have one incentive for all. It would be nice to be able to forecast the customer load, not the entire DWP's load, to know when to call for a demand response. Those customers that are participating in the program, to have a better understanding of what their load is going to be, what is their peak, and what is their performance during a DR. So we can come up with different tiers of incentives to better optimize that for customers. For example, if a customer can give us, I'm talking about commercial DR now, not residential. If we get 1 kilowatt out of a customer with their cooling load in a DR event with a residential customer, we've done really well. But with commercial, we have customers that give us 1 megawatts when we ask for it. So, but we have one incentive tier for all. If we could classify these customers like between 100 kW to 250, 250 to 500, so on and so forth, come up with this, different levels of performance and offer them different tiers of incentives. So that would help us better optimize our incentive structure. Now, when we go to price-based DR, like critical peak pricing or time of use, we can do the same thing with that. The ability to better forecast customers, whether it is energy usage, energy consumption, or their performance while they're in a DR event. So far, it's all historical data. We don't have any artificial intelligence to look at it and tell us what the future performance would be with a high degree of certainty. We cannot just assume if a customer, say, if we call the DR event today, if a customer performed a certain level, we cannot say the next time they're going to do that. We don't have any, analytics to tell us that unless we say, okay, this is what they did last time. As simple as that. This is what they will do next time. But that's not the case here. We see different levels. Different things are happening for the customer. When the temperature is, depending on the temperature, they perform differently. Other conditions, we don't know, type of the customer is different, whether they're, say, for example, an office building versus a factory or a food processing, plant. They all have different, requirements for the operations, but the products, they have different products depending on, how much they need to put out in a given day. That's what we're hoping to do with both with the pricing of DR, if you go that route, or with incentivizing it to optimize that, both profitability to us and to the customer. And that also will help us to better reach out to customers when we do the outreach. So we know who to reach out to for what kind of DR. We can't just blindly go to a customer and say, okay, join the program. If you curtail so much, we give you so much incentive. If we have that knowledge ahead of time, it will give us better outreaching tools to then again, this effort to go, go ahead. Just reaching out costs a lot of money, depending on how you do it. With advertisement, you use, social media, emailing, stuff like that. If we know where we get the most for our buck, then we can kind of focus our outreach to a certain number of customers to give us the amount of, load shaving we need at a given time. That was a very long answer to your question, but those are the things that come to my mind. And having done this for the past few years, and those are the things that come up.
Right. No, that's super interesting. I guess maybe just a clarification question, so that everyone sort of in this group is on the same page. The when you're so I'll do one after the other. You said, and I think you're right. It's very different when you're thinking about residential demand response and commercial and industrial. In one case, it's it's a bit of a it's almost manual. You have almost direct relationships with them. The other case, it's everything is automated. One, just so I make sure we all understand, the nature of these programs. The customers in both categories, in the CNI category and the residential category, how many sort of a customer that's enrolled in your demand response program, the one you're talking about here, how many calls, how many events per year are we talking about? And I think you had a number which was something like 5 to 10 in your slides for commercial.
5 to the most we've had has been with commercial 8, and that was last year because of the heat waves in LA. We usually call between 5 to 6.
And this is a manual phone call from you to each of the 50 people who are on the program.
Yeah, it's an email. It's in the form of an email and a text. Then they confirm whether they're going to participate or not. They let us know ahead of time, so we know what to expect, basically.
Okay, but something like 8 times. Okay, something like I guess at most 8 times per year. And so I guess you say heat wave. So that was mostly in the summer, the 8 times.
Yeah, so far, yes. With residential, I believe last year with the same heat waves, we called for 10 events, but we can do up to 15. That's what the customer agrees to per terms and conditions of the program. Is 15 plus 5 emergency events. If we classify them as emergencies, we can call 5 more events.
Okay.
They're not all emergencies.
And so you said it was automated in the case of the residential. So in the case of the residential customers, you're sending a text message and then they decide to answer, or
no. With the residential, we directly send the signal to the thermostats and adjust the setting.
Okay. So you do control that. Okay. Yeah. No, so I guess one of the questions I was going to ask, I guess, as a follow-up to that, sort of, and how much of a challenge basically is this, has to do with, and I think this is one of the things that you were talking about towards the end of the previous session. But interestingly, when you were thinking about challenges just now, I didn't see it pop up as one of the key ones. I guess if I was taking a couple notes. Sort of big challenges you were bringing up. One had to do with how do you optimize the incentive structure, or the prices, and that one was also linked to a second challenge, which was, I guess the way I think of it is customer segmentation. How do you, when you're thinking about reaching out to customers, how do you decide which customers are going to be good for which type of demand response, and once they're in the program, what kind of incentive structure should I should I give them? And to me, the kind of method that makes me think of is things like clustering. Clustering out. You want to put people into buckets, into groups, and say, these two people are kind of similar, and so they should all get the same incentive program. One challenge that you mentioned at the end of your presentation an hour ago, it had to do with performance uncertainty. And I wonder whether you could comment a bit more on that one. And
exactly.
It's both. Yeah. So when you ask these customers to do something, how challenging is it in the current programs? Not knowing how many or how they're going to respond.
In the ballpark, we know, but then again, when we talk about ballparks, we don't really optimize the process. We can say a customer is telling us that when there is an event, they can approximately give us, say, 250K revenue. But sometimes they do, sometimes they go over, sometimes they do much less than that. But applying AI and some historical data that always exists, because when you have few years, when you've been implementing this for a few years, you have a lot of data sitting there to know how different segments of customers perform. That tells us how much performance to expect, and based on that, we can focus our efforts. I don't want to say marketing at this point. These customers are on the program, on retaining and sustaining these customers. That we offer different incentives for those that are high performers, to keep them on the program and to encourage them to perform better. these are the customers that respond to the price very well. And it's very obvious that they're performing because of that, whatever other consideration they have in mind. Some are just green-minded. They like to contribute to green causes. And that would help us better price our DR. If we just do it without that knowledge, we end up offering, say we need to recruit more customers, we end up offering more incentives to all of them. And come to find out at the end that only maybe 20% of these customers are responding to that incentive level. That if we had been able to identify these customers, we would only focus on those. We would offer that higher level of incentives just to those customers that tend to perform better. So we get more for the money we spend on the program. That's what I mean by optimization. Rather than just increasing the incentives across the board, not knowing that, who's going to pick it up and who's not. All of them will obviously sign up for the higher incentives, but there is no guarantee that they'll be able to perform for it.
Mm-hmm, mm-hmm. So there was a clarification question in the chat for you, Hassan. So from Anish, the automated determined demand response for residential is only through controlling thermostat. That's currently, from what I understood. So right now you're only doing the thermostats, but you're thinking of including EV chargers and other things later on, right?
Batteries, yes, and other maybe smart appliances down the line.
Okay, but today it's just thermostats, and I guess so. On the thermostat, that was sort of I was less thinking of the commercial and industrial customers when I was thinking about the performance, and the uncertainty, whether they're going to respond. I was more thinking about the thermostats, and I guess part of that to me is changing the thermostat is going to depend on the thermostat itself, whether it responds. That's one source of uncertainty, but it's all how much load the thermostat is pulling, or the machine that the thermostat is attached to is also going to depend on how hot it is outside. So like if it's a heat wave, and you're calling demand response because there's because the heat wave is sort of is pressing you, and you send a message to all the thermostats. How well the thermostats respond is going to depend on how hot it is outside, right?
Yes.
So today I'm guessing 25,000 thermostats connected is probably not a huge part of this, but or I guess of how you respond to the heat waves. Do you have a sense, how much does it vary? Like, across the 10 events that you called, the response from the thermostats, is it like single to double? Is it 10-20% difference? The kilowatts that, or the actually I don't know, or is it hundreds of kilowatts? Is it how much do you get from the 24,000 thermostats?
Generally, when we look at the averages per thermostat, we've been getting a number between, say, 500 to 1,000. It's wide, but that range you're talking about, 500 watts to 1,000 watts per thermostat in terms of savings.
So single to double.
Yeah, single thermostat. So we look at the total numbers, we divide it by those that responded, didn't opt out. Then that's how we look at the average performance per thermostat. So we take an average of that 500 to 1,000. We say we roughly expect about 750 watts of savings per thermostat per event. The event could be 2 hours or 4 hours. We generally don't call 4-hour events because we've learned that savings aren't that much because people tend to opt out the last hour or so. So it's better to call for fewer hours and get more performance in terms of energy savings. But 750 per thermostat is a good number on a typical DR day. A typical DR day is when our load is high and temperature is high in mid to high 90s usually.
But and I guess are you collecting data on sort of from one demand response event to another? The how much that changes?
We are, yes, we are, but we're not able to kind of say how much one thermostat had changed over a few events. Oh, I dropped out. What happened? Okay, yeah. Hold on.
No, you're still here. Okay.
Something is happening here. Oh, yeah. Yeah. But because in each event, certain number of customers participate. Those who opt out, that number changes all the time. In one event, say from 28,000 devices, maybe 2,000 would opt out. Sometimes 3,000 would opt out. But we haven't looked at it like that. No. Hopefully, with AI, we can compare one thermostat or track it by whichever means that is possible throughout maybe 10 different events to say that to see when this particular thermostat participated in different DR events, how was the performance of this particular thermostat? We don't have the tools today to be able to see that, but we can look at averages. Averages are about the same, but individually we don't know. Then again, customer segmentation, to be able to identify a group of thermostat and track their performances over maybe 7, 8, 10, or 15 events in a season.
Right, yeah, ideally, yeah, that's what, yeah, you'd like to know, yeah, different parts of the customer base, how do they perform? So there's a question from Vijay. I don't know if this is a question for Hassan. Maybe Vijay, if you can unmute yourself and tell us, is this a more general question, or is this specifically for the demand response programs we were talking about, this question?
This is more general question. I know we're talking, more detail here, specific use cases, but in general, I'm from Exelon. I don't know whether anybody works here with Exelon, but we have large program AI internally, and we use, some of the systems. And I was just wondering if people here, they tend to use like cloud systems more for their AI modeling kind of, use cases, or they have homegrown platforms built on, graphic chips and all those things. So that's what I was wondering.
So I'm on the academic side, so I don't have an answer to that question, but I see quite a few people in the are in the meeting, so I'm hoping someone can chip in.
Yeah, that's fine. Means, yeah, it's a general question.
No, but so is there someone here who's on the industry side who's using AI modeling platforms and who could comment on, sort of, is this better in the cloud? Is this better to do it in-house? I'm guessing there are pros and cons. And what good technology companies are you using? Someone was saying something, but then maybe had an audio problem. Okay, then. So I guess the answer
Josh,
from
I can jump in.
Who's that? Jeremy. Oh yeah, go ahead.
Yeah, this is Jeremy. Yeah, I can jump in and talk a little bit about what we're doing. So we have a data science platform that we put in. It's on an Azure cloud. We're able to log in. Anyone at EPRI or our contractors are able to get in. We have data that's securely stored there, and it's one of the items where we can control very closely and very tightly who has access to what data, and no one is allowed to, even the people who have access to the data can't take it off site. And we do that simply for the fact that we work with a lot of utility data that can be sensitive, so we have lots of controls and restrictions in place. In terms of AI platforms, we have a lot of the standard, Python, R, Studio, SQL, and various other systems and tools that we use. So we do a lot of cloud computing simply for the fact that, and I'm going to steal a quote from Wesley Jones from the National Renewable Energy Lab. He said that our most secure systems are in the cloud, and I would agree with that, because even on-premise systems sometimes can have more people as they come through the building that can get access to them, or not as tightly controlled as some of the cloud solutions are. With cybersecurity concerns at the forefront of pretty much everything everyone's doing these days, the cloud solution providers are really they're leading the way in terms of cybersecurity and access to the data. So hopefully that answered at least some of the question you were looking for.
Yeah, no, that answered the question. And you in fact actually talked to the concerns that, I was thinking, all of those security and data privacy, because we have data for 10 million plus customers and we do all the modeling. We do use, I think we might have collaboration with Stanford or any other, but I think when the time comes to, basically put them in practice, it's always difficult choice of the platform. So this is very helpful. Thank you.
I mean, I can definitely chip. So you were saying Stanford. I'm at Stanford, and I do a lot of work with with the cloud systems. I would just to comment on that, so I'm definitely not an expert in terms of security. I can talk to sort of the sort of the easiness of use of working on these environments. And I will say that from a university perspective, it's pretty easy, and then I mean, and I guess we'll trust Jeremy if Jeremy says it's secure to to access these cloud systems from wherever you are. And I've worked with a couple companies like this before, where basically, sometimes there's a VPN that you have to log into, or there are credentials, and then
Yep.
so at this point I've worked with AWS, Google Cloud, Azure. From my perspective, they're all very similar. They have slightly different tools. They're a bit different, but but they make it very easy to access something. And I remember sort of working with I think it was PNL on a project 4 or 5 years ago, and I think this was from data from the Bonneville Power Administration. I'm not sure, but basically it wasn't on this kind of system. There was a whole process you had to go through to start working with the data as an academic, and that made things much more complicated than than it is in these environments. So I can't really talk to the security side of things because I don't know much about that. But from the sort of sharing perspective, really nice. And I know that there are all sorts of controls that you can put in place. They're like in the AWS, they're called roles. Where you can decide, different people, different parts of the organization get access to different resources, and you can have pretty fine-grained control on who has access to what. So I'm definitely a big fan of these cloud computing systems.
No, that's good to hear, and that is something we are going in that direction, and this kind of reinforces that, because we used to treat this data as our kind of baby, right? Crown jewel. We can never let it go, but I think things are changing, and these platforms give security, not only security but the power, right, to process the data, at least initial training of the models and everything. So this is good. Thank you very much, both of you.
And actually, I would go beyond, so this part of the discussion was focused on data, so there was a comment or a question earlier from Anis in the chat. I think this also applies to models, and I guess so the question from Anis, I don't know if I'm pronouncing that right. I'm sorry if I'm not, but so whether if you have a proven model from one utility and you retrain it with the data set from another, can you get the same result with a bit of tuning? And I think there are two things there. One is what Priya, so Priya isn't with us anymore, but what Priya was saying earlier, which I think is very right, is there are some contexts in which that won't work, if the data sets are different. And I think the example that Priya was giving was if you're using drones to identify where power lines are, and you're doing it for one utility, and then you move to a different geographical region where just the lines don't look similar. They're underground, or well, then I guess that's the extreme example of something where you can't really reuse the model from one place to the next. So I think there are structural questions there. But if everything is the same, then that's something that that would work really well. You take the model, train it somewhere, and then once you've done all this work on developing the model, you can put in a new data set, and what you're passing around is not the data. I know of people who are working on this, for the privacy aspect of it. What you pass around are model coefficients, basically. That's the simplest way of thinking of it. Say the algorithm that you're training is a linear regression. So you're fitting y equals ax plus b. The y and x pairs that are the customer, the sensitive customer data, you don't want to share that, but you can share the a and the b. And so if you're just passing those two parameters around and retraining them, and changing them slightly for someone else's data set, that's also very secure. And and I think where I see this tying into the whole discussion about the cloud, and versus something that's in-house, and very local, is that if everyone's using a standardized set of tools that are the same for everyone, it just makes sharing these much easier. Jerry was saying they use at EPRI, they use SQL, they use R, they use Python. If Jeremy sends me a link to a GitHub repository that has a Python package, I can just clone that onto an AWS system, and sort of use that directly. And there isn't so much of the onboarding that you would have if the development that Jeremy went through was on one kind of system and I was on another system. if we're all using cloud-based resources, that just makes things much, much, much easier. Okay, so we have, sorry, so there was someone wanted to jump in?
Hey, John. I think I was going to say the same thing as you. Just a quick time check. We've got about 10 minutes left in the meeting, so might be time to kind of coalesce together around the grand challenges and start to kind of record where we want to go and how we want to move forward.
I guess quick, yeah. So we were doing some of that earlier. Maybe since we have you in the meeting, Jeremy, just a question. So how do you want us to bring these back? So I was taking a few notes. Is the idea to coalesce these, or is there a reporting that I do at the end?
Yeah, I think what we're going to be doing is you'll just bring those together. You'll send them to us, and we'll kind of bring those together into the final meeting report, and that report will be shared with everyone who is here in the meeting. So everyone will get access to that. Okay, great. Yeah, and I guess I can start by doing a bit of a recap on sort of challenges that we've identified, and and then see if if participants in the meeting can tell me if I'm missing something, and if there's some if we have a bit of time left after that and we want to talk some more, then we can do that. So so I think what we started with was the set of challenges, the set of 3 challenges, more from the academic perspective that Priya gave us in her talk, and those were those 3 challenges were, if I summarize, were how do I take into account physical constraints in machine learning models, or how do I have machine learning AI play with physics of the real world? Because a lot of the tools that were developed in the machine learning world are for applications where fully respecting the physics is not something that is an absolute necessity. But for many applications in the energy system world, in power systems, for example, it is an absolute necessity. You really do want the system to work. So how do you integrate that? And then there were two other challenges that I think we talked about. We talked about through examples with Hassan on demand response, and before Hassan and the rest of the LA team joined, we talked about on tackling different problems, and those 2 were so interpretability. So how do you design algorithms that are easy to interpret? And I think that sort of the case in point for that was the whole discussion around demand response and customer engagement that Hassan kind of walked us through. But on the how do you do customer segmentation? How do you optimize for the incentive structure for different customers, things like that. So and that I really think is the interpretability question. And then on the other on the other end, there was something that we talked about a bit before the LA team joined, which was the what Priya called the distribution shift, which was and which was if you train models in one context and you want to apply them in another context, how do you do that? And I think that applies to when I say that, it's a bit abstract, but really, to give concrete examples of what I'm thinking there, there's things like if you're planning a power system based on variables that have a certain distribution today, and that distribution will be different later on, how do you do that? Okay, so I have weather data today, but that weather data isn't really informing me for the future. So somehow, when we're doing integrated resource planning at LA.DWP, we have to take that into account, and that's a really big challenge. And so that's the temporal aspect of it. And then the one that I completely missed, and that I think Priya brought up, and then someone, I think I guess there was 2 other dimensions. One was brought up by, I don't see her here anymore, but Cheryl, I think, brought this up with the battery technologies. Was so if you're optimizing batteries, the batteries are going to change over time. How do you take that into account? How do you have algorithms that are good at optimizing batteries, given that the chemical processes that are playing in the batteries are changing? So that's another example of a distributional shift. And the third example, which was Priya, was the one we were just talking about. Was I guess the example with the drones and the power lines. I'm training a model, with images, but then I move to a different. I want to use the model that I trained with one utility somewhere else, but
the data I trained on had a very different distribution from the other model. So I actually think that's maybe one a way, a good way we can sort of lay out the challenges that we talked about in this session. Those sort of three axes that Priya started us off with, refined with a lot of the things that came here. And I guess so. I'm checking the time. We have something like 5 minutes left. Maybe are there things I'm missing here? Are there challenges that we want to bring up that we haven't really brought up here? I guess that there was also a bit of discussion around these cloud computing platforms, but I think that was less of a challenge, a bit more of a tangent. Are there other things?
Jacques, one thing that I'll say, and this is actually coming from other people, not so much me. Unfortunately, this person couldn't make it to the meeting today, but really it ties in several of the concepts you talked about in terms of customer segmentation, distribution shifts, battery technologies. But it really comes around with grid integrated buildings in terms of bringing together all of this data and doing something with it. To where we can start to, we have millions or tens of millions of buildings around the world that are taking up something like 45% of the total energy of the electric grid. So if we can do something to help reduce or shift the energy usage, we can combine that with the battery technologies, there could be a huge impact that we have on overall decarbonization and demand response. So I'm going to throw that one out on behalf of a couple of utilities that had mentioned that to us.
Yeah, and I guess so it's true. We didn't talk about that one. So I actually know that one of your colleagues, Penn, is very interested in that as well. And the only thing, so it's true. We somehow I managed to steer away from grid integrated buildings. The big project I'm working on right now has to do with grid integrated buildings on this, and doing experiments right now on the Stanford campus with some of their buildings. So this is a topic I'm very interested in, and I guess that's another. Actually, I'm thinking, all three of the sort of the axes, sort of all three of the types of challenges we talked about, I think, have really good examples in that space as well. I guess one of the ways I think we can structure these grand challenges, at least from this session, the grand challenges, is that there are sort of two axes. There's sort of conceptual challenges, and there's challenges that more with the applications, and so we have these three categories of conceptual challenges, and then for each of them we actually talked about quite a few of the what this means in real life, this conceptual challenge. So we don't have too much time left, but maybe apart from Jeremy, if there's someone else who wants to jump in with a challenge, a difficulty that we haven't really talked about.
A question I believe I asked this question while I was answering a question put to me about battery technology in terms of DR. What is the latest out there? What is it we can do with these batteries today in terms of controlling them? What parameters we can control? My assumption would be, can we control the discharge rate when we use these batteries? Say remotely, we can put them in a mode that wouldn't discharge as fast or would discharge quickly to use the energy so they can charge them again. Something along controlling these batteries that makes them more usable for DR application.
Yeah, you're right. I actually remember that question from when you were talking, but it's true that it was a bit of a long answer, so I'm not sure everyone got that question. I think so I don't know if someone wants to jump in on that one. I had so I guess my thought on that is I don't know about specific technologies. I think one of the difficulties, and on the research side, I definitely know quite a few people who are working on this topic, is how do you build controllers that are agnostic of what kind of battery technology you have? Even is it lithium ion? Is it flow? Is it something else? Is it sort of the Tesla Powerwall? How do you have that software layer that's in between? And you were asking what are the parameters that you're controlling? At least the people that I know that are thinking about this are actually not thinking that you would want to control the parameters of the batteries directly. not only because it changes from battery to battery, but also because of privacy concerns. You know, you probably wouldn't want to be. So the question is there an intermediate software layer that, you know, that's sitting on top? You know, kind of like there's an intermediate software layer when you're talking to the thermostats, and that's something you would, you know, a gateway that you, LADWP, would be talking to, and then that would be deciding for each of the different batteries what to do. What I don't know, you know, and I guess I don't have enough knowledge of the industry, is whether, you know, are those just solutions that people in the research community talk about, or is there something that exists? So, you know, to me, that one's a bit of an open question.
Okay. Yeah, that would help a great deal with designing battery-focused DR programs.
Yeah.
If you know, you know, the same software we use, for example, through a vendor to control those, say, thermostats, we're able to have a pre-cooling with them for a couple hours, maybe 1 hour, then first dial it down for pre-cooling for a certain period of time, then dial it back up for, you know, another period of time. Then that gives us the flexibility to get the savings we want out of it while minimizing the impact on the customer. So they don't, you know, just get too hot and, you know, just get out of it or opt out. So if that happens, then we have failed in what we intend to do. So if you can do the same thing with batteries, control the discharge rate to make it, you know, last longer with whatever software, because charge and discharge alone really won't cut it for DR. It'll do it in a crude way, but at the end of the day, it's not really the optimum way of doing this. We need to find a way to use it more intelligently.
Right. Okay. So yeah. So I think we're at time. But so I, you know, I guess on that one, if anyone has, you know, a great, you know, a good solution for Hassan, you know, I guess a shout out to reach out to him or to the rest of the team. And I think, Jeremy, everyone can find everyone's contact information on the event website.
All the speaker contact information is there. I don't think we have everyone that's attending there. We have, I think, over 500 people registered. So,
so we're not really
looking to get in contact with someone. We can help facilitate that, though.
Okay. So if someone has something for Hassan, then yeah, then I guess reach out through the event organizers. Okay, yes. And then, you know, I guess I don't want to stop the people on the West Coast from their lunch and on the East Coast from their afternoon. So thanks everyone for coming to this breakout session. I definitely learned a lot and had fun. I hope everyone here did too. And I think, so Jeremy, I think this is the end of the day, right, for the event. So I don't think there's anything after this.
Yes, that's correct.
Okay, so see you all tomorrow. Well, I guess through the interface.
Okay. Thank you. Thank you very much.
I look forward to seeing you tomorrow.
Okay.